In this video, we'll look at naive Bayes from a more practical perspective, and I'll talk about how to train a naive Bayes classifier using bag of words features. I'll cover how to handle unknown words and stop words, walk through the formal algorithms to train and test your model, and then go through a case example so we can see how a naive Bayes classifier might be trained to perform sarcasm detection on a tiny corpus. When we train a naive Bayes classifier, we need to do two things. We need to find the prior probability for each class, and then we need to find the likelihoods for each feature occurring given each class. Fortunately for us, figuring out both of these things is pretty straightforward. To find the prior probability for each class, we just need to figure out what percentage of the instances in our training set are members of each class. So if we're doing sarcasm detection, we'd probably need to know what percentage of the training instances were sarcastic and what percentage were non-sarcastic. To find that percentage, we just divide the number of instances in our training data belonging to that class by the total number of instances in our training data. To compute the likelihoods of features occurring given specific class labels, we can use something that we already learned about previously and find the maximum likelihood estimates for those features. Now, for our features right now, we're just considering a bag of words. So for each word, we'll just need to figure out the fraction of times it occurs overall from among all words in class C. To do that, we'll take the number of times that the word occurs in class C as the numerator and divide it by the sum for all words in the entire vocabulary of the frequency of all words in class C. Now, in doing that calculation, there's a fairly good chance that some words won't ever occur in class C in the training data. You may recall that zero probabilities can be problematic. This is because when they occur, since you're multiplying them with all the other likelihoods, your entire class probability will automatically end up being zero. Fortunately, we've also already covered many possible solutions to this as smoothing techniques. The simplest smoothing technique that we saw previously was Laplace smoothing, so we'll go ahead and use that in our examples here, resulting in an updated equation for the probability of a word given a class. So, smoothing solves the problem of some words from the training data vocabulary not being present in every class in the training data, but it doesn't solve the problem of some words from the test set never having been present in the training data at all. There are a couple different strategies for handling unknown words, and for now, we'll just use the easiest in our case example. We'll go ahead and ignore any words in the test data that were not also present in the training data. Stop words are another thing we'll want to address when training our naive Bayes model. In natural language processing, the term stop word just refers to a really common word that doesn't carry much or any meaning that is relevant to the task at hand. Stop words can vary between tasks and datasets, so what would be considered a stop word for one task might not be considered a stop word for others. Whether or not you want to ignore stop words also varies on a task-by-task basis. In a lot of cases, stop words are pretty unimportant and they can just add noise to your data because they occur with equal frequency across all classes. But for some tasks, stop words are actually pretty informative. For example, for spam detection, the presence of stop words can actually tell you a lot about how likely it is that an email is spam or not. There are two different ways that people define stop word lists. Sometimes they do it automatically, so they just order their vocabulary by training set frequency, and then they say that like the top 50 most frequent words are stop words. Other times they do it manually using a predefined list. The latter approach might be more common just because some popular NLP libraries have built-in stop word lists that can be accessed really easily through a function call. So ultimately, we end up with the following algorithms for training and testing our naive Bayes classifier. To train the classifier, we loop through each class and first calculate the prior probability for the class. In this case, we do our computations in log space to avoid underflow errors, so we'll take the log of our prior probability. Then we'll create a big sort of super document containing all of the instances from class C. We'll loop through each vocabulary word from our training set and count the number of times each word occurs in the super document for the class. We'll plug this value into our likelihood equation with Laplace smoothing, and then take the log of that. Testing a naive Bayes model is even simpler. For a given test instance, we'll again loop through each class. We'll get the prior probability for the class, and then loop through each word in the test instance. We'll check to see if the word is in our vocabulary since we're ignoring words that weren't present in the training set. And if it was, we'll find the log likelihood for the word given the class based on what we computed when training the model. And then we'll add that to our running total since we're working in log space. If we weren't, we'd multiply it with our running product. Finally, once that process has been done for each class, we just select the class with the highest running total. I'll go through an example now to show how this algorithm works in practice. So let's say we want to build a sarcasm detection model. We have a small data set with 5 different sentences, and we have labels for 4 of them. We want to train our model using those 4 sentences, and then use it to predict the label for the 5th sentence. We'll go ahead and organize the instances in a table divided into our training set and our test set. So to train our model, we'll first need to figure out the prior probability for each class. We have 2 classes here, so first let's go ahead and find the prior probability for sarcastic. We see that there are 2 sarcastic instances out of our total of 4 instances in our training set. There are also 2 non-sarcastic instances. So our prior probabilities are 0.5 for each class. This means that based on class probabilities alone, the test sentence would be equally likely to be sarcastic or non-sarcastic. This means we have a balanced training set, so let's move on to computing likelihoods now. We have 10 words in our test sentence if we just do white space tokenization, but taking a closer look at it, we decide that we don't really want to consider stop words. We also want to make sure that we remove any unknown words from the equation. We'll remove stop words first, so we check our stop word list and end up removing she, was, for, and him. Next, we'll move on to unknown words. We see that the word told never occurred in the training set, so we'll go ahead and remove that too. So we're down to 5 words now. We can go ahead and compute the likelihoods for those 5 words. If we were training our model in full, we'd want to compute the likelihoods for every single valid word in the training set. But here, since we know for sure that we only have this single test instance we're interested in, we can get away with being lazy and just computing them for our 5 words of interest. So let's start with the word Natalie. We find that the word Natalie occurred 1 time in the set of sarcastic training samples and 1 time in the set of non-sarcastic training samples. We're doing Laplace smoothing here, so to compute the likelihood for Natalie, given that the class is sarcastic, we'll have 1 plus 1 in the numerator. In the denominator, we'll have 15 because there were 15 valid words in the training set belonging to the sarcasm class, plus 21 because there are 21 unique words across the entire vocabulary. So it'll be 2 divided by 36, which equals 0.056. To compute the likelihood for Natalie, given that the class is not sarcastic, we'll still have 1 plus 1 in the numerator, but in the denominator, we'll have 12, since there are 12 valid words in the training set belonging to the non-sarcastic class, plus 21 again, because there are still 21 unique words across the entire vocabulary. So we'll have 2 divided by 33, which equals 0.061. We'll continue on and also compute these values for the second word. We compute likelihoods again for the third word, finding that in this case the word so with 4 O's didn't occur at all in the training data for the non-sarcastic class, so it's a good thing we're doing smoothing. We see that that's also the case for the word totally. And finally, we compute likelihoods for happy and see that it occurred in the training data for not sarcastic, but it didn't occur in the training data for the sarcastic class. So we have our likelihoods now, and we'll go ahead and put them in a nice little table to make things organized. And now we can go ahead and do our classification. We haven't been doing log probabilities, so we'll multiply our prior probabilities and the relevant likelihoods together for each class. So our probability for the sarcastic class will end up being 0.5 times 0.056 times 0.056 times 0.056 times 0.056 times 0.028 for a product of 1.377 times 10 to the negative 7th power. Our probability for the not sarcastic class will end up being 0.5 times 0.061 times 0.061 times 0.030 times 0.030 times 0.061 for a product of 1.021 times 10 to the negative 7th power. So actually the class probabilities are very close to one another. However, the first probability is ever so slightly higher, so we'll end up assigning the label sarcastic to our test instance. So now we've seen how to train and test a naive Bayes classifier using bag of words features.